Hello, our presentation is about how a helium neon laser works, but before we get started on this more specific example, we will talk about how lasers work in general, and then we will graduate to the helium neon laser.
The whole point of lasers is that you get a very high intensity beam of a very specific set of wavelengths. Of course, it is possible to do this with just a high power light bulb and a filter, but it's extremely inefficient as you're taking out almost all the light and the beam you get is therefore of very low power. How lasers work is all contained entirely within the name: light amplification by stimulated emission of radiation. To understand this, we must first look.
You probably already have some basic knowledge about atoms, including the fact that they consist of a nucleus surrounded by electrons. These electrons are in their own discrete energy levels, or orbits. Quantum effects acting on these electrons mean that they cannot exist in the dead space between the energy levels. If a photon of the correct energy interacts with one of these electrons, the electron can be stimulated and lifted into a higher orbit. This electron is then said to be excited, and it has to look for ways to lose its newfound energy. The way it loses this energy is what we're interested in, as dropping down to its previous energy state, it releases a photon with exactly the same energy as the gap between the energy level E2 and E1. This is spontaneous emission.
So the overall aim of lasing is to cause stimulated emission, as stated earlier. To do this, the electron must have previously been lifted into a higher energy orbit, and it must be stable there for a certain length of time. This is called a metastable state, and here you have an example of an electron in its metastable. A photon from somewhere else outside the system has to interact with that electron, causing it to fall down. In doing so, that electron, as stated earlier, will release another photon as well as the incident photon. Now, if you have a whole bunch of these atoms with the electrons in metastable states, all it requires is one electron to fall down, release a photon, which then sets off a chain reaction. One photon comes along, interacts with the electron, which falls down, releasing the stored energy as a photon as well as the incident photon, and each of these then goes on to cause their own reactions, as shown here. In addition to all of this going on, the photon given off is in exactly the same phase, and by that we mean that the troughs and peaks are in exactly the same place in time, meaning that there is constructive interference which gives a higher intensity of beam. This is the amplification of the light signal.
In a metastable state than there are in their ground state, because otherwise there would be more photons absorbed than are released, so you wouldn't get amplification of light. For this to happen, 3 or 4 lasing level substances can be used in order to invert the population of metastable atoms, therefore leading to higher numbers of metastable atoms in levels E3, E4, as shown in this diagram. There isn't enough time to go into this in detail in this video, so we will have to just assume that this is true.
So for this amplification of a signal to take place, it has to take place within a reflective cavity. Here, 2 mirrors are placed at either ends of a chamber, one which is 100% reflective and the other is only 90% reflective. This second mirror therefore lets a small amount of the light created out, which is the laser beam, as you know.
So effectively the basic setup of a laser is this. You have an active medium containing atoms, some form of energy input, in this case a flash tube that would release light. The flash tube, when it fires, releases photon light into the active medium, and this excites the constituent atoms within it. These constituent atoms then release photons spontaneously by the process talked about earlier. Some of these spontaneously emitted photons run in a direction which is parallel to the lasing axis, therefore bouncing either end of the active medium off the reflective surfaces, repeatedly as they move back and forward between the two surfaces, stimulating further emission of photons from the constituent atoms. Eventually, once a sufficient level has been reached, monochromatic single-phase light will leave through the partially reflective mirror. This light coming out is laser light.
Right, so now we've been through lasing in general, so we're going to talk specifically about helium neon lasers. Here, the energy input is made by passing a high voltage through a mixture of, well, rather unsurprisingly, helium and neon gas. Electrons here are pulled off atoms, creating a plasma inside the tube, and are accelerated towards the positive terminal. On their way, the electrons hit into helium atoms, causing them to become excited. Some of these helium atoms then crash into neon ones, transferring the energy across.
Excited electrons in the neon atom then fall down to a specific energy level, releasing a specific wavelength, in this case 632.8 nanometers. The neon then undergoes two further decays back to its ground state through interactions with other things within the laser.
The downside of this type of laser is the low power output because of energy losses within the system, because not all of the light is constructive, it all bounces around, and some of it's absorbed in fact within the plasma in the tube. So it's got a very low efficiency of less than 0.1%, so for a high power one you've got to be prepared to pay.
What helium neon actually do. Helium neon lasers are now fairly commonplace. They are found in labs, and despite the fact that there technically are better lasers out there, they have become fairly common because of their ease of use and relative cheapness. They're widely used in areas of science such as spectroscopy. Spectroscopy obviously is looking at the chemical makeup of materials by investigating the radiation they give off when they are placed under them. They also found a use in the pre-MP3 days, where they were found very often in CD players. Obviously, in the time of the iPod, they have somehow lost this function. So here you have the light amplification.
And here you have the interaction with tissue.